Friends, welcome back to this course. So far we have discussed turbulent combustion. Essentially we have discussed the beginning from at the beginning of this part of the course on turbulent combustion. We have discussed essentially the physics of turbulence, the modeling turbulence, how you can basically use the RANS, the Reynolds average Navier-Stokes equation, to get an idea about the mean flow field, and how this, when you average these equations, this problem, the closure problem, emerges. And then in the last class you have seen that how using this different eddy viscosity hypothesis we can essentially have this kind of closures. We have the eddy viscosity closures by using the mean strain rates. We can use them to close the Reynolds average Navier-Stokes equation. And we have also seen how for reactive scalars how problems emerges in terms of closure of the reaction rate, the mean reaction rate, or the reaction rate in terms of the mean temperature or the scalar transport. So there are problems. So and we have discussed some simplified models, okay, in generalized simplified models like the eddy breakup model, the eddy dissipation concept, the eddy dissipation model, different things, how those can be used to model turbulent combustion. But those are very preliminary and rudimentary models, and actually the field of turbulent combustion has progressed far beyond that. So in this course we will give you a glimpse of the modern developments in turbulent combustion, and we will start that by using turbulent non-premix combustion. So you have seen that that in the beginning of the course we have essentially distinguished combustion in terms of non-premix flames and premix flames. Non-premix flames are those in which the fuel and air are separated as it enters into the combustion, as it enters into the combustor. So we have done actually the analysis of one dimensional laminar flame or the one dimensional chambered flame, where the fuel and air basically were separated by two on the two sides, one on the left, one on the right, and the flame was formed somewhere in the middle. Okay, and then we did an analysis of that, and we obtained linear profiles of temperature, mass fraction, etc. And then we did the droplet combustion also. Okay, now but here in this class we will take up turbulent non-premix combustion, and this is divided into essentially these three parts. We will go with the introduction. We will say where you can essentially encounter turbulent non-premix combustion. We will then introduce a very important concept called the mixture fraction. Okay, this we have not introduced, but this we can use in laminar flames also, but essentially the importance of this and the beauty of this concept of mixture fraction becomes evident in turbulent non-premix combustion. And then we will use those ideas of mixture fraction to essentially do this analysis or modeling of turbulent non-premix combustion. And the majority of the material in this course is taken from these two books, mainly Turbulent Combustion book by Norbert Peters, published by Cambridge University Press, and this combustion theory by Norbert Peters from the CEFRC, Combustion Energy Frontier Research Center, Summer School, Princeton. That these lectures were developed in 2010, and this is, I believe, is available online free of cost in the CEFRC website. Okay, so these are both the references that we will follow for this part of turbulent combustion, turbulent non-premix combustion, and later in the next class turbulent premix combustion, in the next module turbulent premix combustion. So in this module we will focus on turbulent non-premix combustion. Now why we will study that? As you see, this course is on combustion in air breathing aero engines, and of course the gas turbine engine and ramjet engines are two very important parts, and as such in the gas turbine engines, the most of the aero gas turbine engines historically have utilized turbulent non-premix combustion. Okay, so essentially this you see is essentially the gas turbine combustor. Okay, so after the flow enters from the left to right through the compressor guide vents, it passes through a diffuser section, okay, where in this part where the pressure is slightly recovered, and then it passes to this set of swirlers. So when we will go into the main when we will go into discussion about the gas turbine combustors, this details of these combustors and this architecture will become more clear. But essentially here you will see that the fuel is injected in a liquid sheet through this central injector, and then this liquid evaporates. Then this liquid sheet essentially breaks up, and then this droplets are formed, large droplets are formed, and then this large droplet breaks up into small droplets, and then the small droplets evaporate, and this these droplets are essentially of jet fuels. So essentially this liquid evaporates, and then it basically forms a nearby cloud of this mixture of this fuel essentially, which then mixes with the air, and sometimes the point at which it mixes with the air, the mixing is not very efficient, and essentially the flame that you have is a non-premix flame. Okay, so in gas turbine, aero gas turbine engines, typically flames have been historically has been non-premix flames, except with some recent developments which we will discuss now, which we will discuss a little later. And you see here you have the primary zone, essentially the main combustion will be essentially will be here. So here you have the flame like this. After coming out of this injector, the flame will be something stabilized along here, and this is essentially a non-premix flame or a partially premix flame, though it can have some premix segments also, but predominantly this type of classical gas turbine combustors utilized non-premix flames. So for understanding gas turbine combustion, or for in IC engine, if you want to understand diesel combustion, then this non-premix flames are typical examples of the kind of combustion that happens in this typical engines of non-premixed of this gas turbines. Okay. So of course there are something else also, like these cooling holes, which essentially cools down the hot gases, so that the turbine temperature can be controlled. We can have a limited turbine entry temperature, and in ramjet engines also, you see here through the intake, as the flow comes in, it is essentially through the shock trains. It's essentially a supersonic intake, and then it becomes subsonic through this formation of the series of shocks, and by the end time it enters into the combustor. These are essentially subsonic flow, and you have a flame stabilized in this flame holders, and this fuel is injected right upstream of these flame holders, and typically you get a decent amount of non-premixness in this flow, and the flame that you get is essentially a non-premix flame also. So ramjet engines and gas turbine engines are good examples of non-premix flames, though there are some there are some regions also where you get premix flames, but a large fraction of the flame is also non-premix flame. Okay. So as you know, in non-premix flames, mixing is very important. So yes, we will see that how we can essentially model mixing in non-premix flames. As you remember, if when we did the analysis of the 1D non-premix flames, we essentially assumed that the chemistry was infinitely fast, and and essentially the flame parameters were essentially mixing controlled. And here also we will see that how, while modeling turbulent non-premix flames, this hypothesis of the flame time scale being essentially controlled by the mixing, that the mixing being the rate limiting step, that hypothesis essentially holds here also. On the right hand side, you have an example of a lean premix pre-vaporized combustor. These are the very modern combustors which are used in modern gas turbine engines, like the TAPS twin annular premix swirler combustor, which powers essentially the Boeing 787, as you know. And here also you see that yes, this has got main premix flame branches on the two sides, but it has also a pilot flame which is essentially a non-premix flame. Okay, so this as you again see that this non-premix flame is also present in the very modern gas turbine combustors. Now, as we have, if you remember, we discussed that there are disadvantages of non-premix flames, because you essentially cannot control the temperature. The temperature is always essentially the stoichiometric adiabatic flame temperature, unless you have like something like this cooling holes here, as we have seen here downstream. But other than that, this temperature is high. It's locally at the flame location, its temperature is adiabatic stoichiometric adiabatic flame temperature, and as a result of that, all the pollutants are also being formed. Soot, NOx, etc. Okay, so that is the main disadvantage, but we will see later that non-premix flames are much more robust than premix flames, because here you do not have a velocity scale like something like a flame speed. So essentially it can be stabilized in fast flows also, as long as there is mixing. Okay, so once again this fact that the non-premix flame is essentially a mixing control phenomena has an advantage, that it is much more robust and it does not respond to the flow oscillations as much as a premix flame does. So that is one big advantage. And so non-premix flames has been very prevalent in all these aero gas turbine engines, and even in scramjet engines flame is to a large degree non-premix, though there are premix segments also. So one thing you must understand this in the actual gas turbine engines, that flames are also though they can be like predominantly non-premix, there are like segments, there are like regions which are premixed or partially premixed also. Okay, so it's a mix of these two, and but I mean combustion modeling historically has progressed in a way that it models non-premix flames and premix flames separately because of their distinct properties. So to understand though how to model essentially a flame in a combustor which is predominantly non-premix, we will go into this course and we will go into this detailed analysis and see how to essentially what are the approaches by which non-premix flames in this type of engines in this type of combustors can be modeled. Okay. So in a lab what you encounter, what you of course to make models you cannot use directly go to a gas turbine combustor. So what you do is that what people have done is that they have basically done detailed measurements in these kinds of simple non-premix flames, which can be like a jet flame, counterflow flame, flames in mixing layers, and shear or salt stabilized flames. Okay. So these are the typical flames people have studied in laboratory. So the idea is that you develop detailed diagnostics using different kind of optical methods. People have done detailed measurements of the flow, temperature, species, etc. Of these different kind of flames, and then they have used different modeling approaches with which they have validated the experimental data. Okay, so then the idea is that these tools that one develops for modeling the simple flames, once they are robust and rigorous and we have developed sufficient confidence in them, then these can be utilized towards essentially modeling the actual non-premix flames that happens in a real gas turbine engine or a real ramjet engine or a real scramjet engine. So that is the approach. Okay. So people have really done these kinds of flames in their lab. So you will see this is examples of different kinds of counterflow flame, jet flame, etc. And there are flames in essentially mixing layers. So jet flames, counterflow flames, flames in mixing layers, and these are the typical these pictures come from the turbulent non-premix flame workshops where essentially people have done different kind of flames, these simple jet flames, piloted jet flames, bluff body jet flames, flame stabilized by bluff body, and so all stabilized flames, and using all these they have done detailed measurements in them, and then people have used them for validating the different numerical simulations. Okay. So from here on we proceed on to essentially the turbulent non-premix flame modeling. First we will do essentially introduce this mixture fractions concept or this mixture fraction space in a laminar non-premix flame. So we will do a little bit of go back a little bit into this laminar flame, or this is generalized essentially, but we will go back to this once again to this apply this mixture fraction ideas to the 1D non-premix chamber flame that we discussed. Okay, so we will see how the mixture fractions concept can be applied in those kind of simple configurations, and then utilizing them we will proceed to essentially see how the mixture fraction helps a lot when you go for modeling turbulent non-premix flames. Okay, so what does the mixture fraction, why does it come? Okay. So as you see that in non-premix flames, the basic idea is that there is a very basic underlying embedding idea. The embedding idea is that the chemical reactions are much faster compared to other rates. Okay, chemical reactions are faster compared to other rates. Therefore, diffusion. Okay. Diffusion in when you say diffusion, it means that diffusion of both heat as well as species. So species as well as thermal diffusion is essentially the rate determining process. It is the rate controlling process, and it is the rate of diffusion that governs how much your combustion rate will be. So we have to essentially, the idea is that we need to find out a suitable conserved scalar. Okay, as you remember, the conserved scalar is one in which does not have a source term. Okay, so which there is no source or sink term, so that one is a conserved scalar. So we need to obtain, first we need to define a conserved scalar and obtain that a solution for that conserved scalar, and so that we can use that for describing this mixing, which is the rate determining process. Okay, so that is the idea. So in search of that conserved scalar, we go into define this mixture fraction. So, what is this mixture fraction? The mixture fraction, okay, the mixture fraction is defined in this manner, that if you have a two feed system. What is a two feed system? Suppose you essentially have a nozzle like this, okay. At the center of the nozzle, this is an axisymmetric nozzle, okay. So, you have a fuel, and on the sides you have another annular nozzle, annular cylinder through which air is coming out, okay. So, that is a two feed system. So, the two feed system means basically you have a feed of, you have one feed line of fuel, we have one feed line of air, and of course, this fuel and air are not mixing, okay. So, then the mixture fraction definition is that in such a two feed system, the local ratio of mass flux originating from fuel feed to the sum of both fuel and oxidizer feed mass fluxes is defined as a mixture fraction, okay. So, you see that it is the local ratio of mass flux originating from the fuel feed to the sum of both the fuel and oxidizer mass fluxes. So, suppose the fuel mass flux is M1, we will use a symbol subscript 1 for the fuel feed, and we will use a subscript 2 for the air's feed. So, the mass flux from the feed line is M1 and the mass flux from the oxidizer line is M2. So, sorry, this is M2. You see, but that is M1, this need not be pure fuel, it can contain inert also. So, this is a fuel feed where you have to have a well defined mass fraction for the fuel, it need not be always 1. Similarly, here the oxygen mass fraction need not be 1, if it is air or any other things, here also there can be oxygen and nitrogen can be present in different proportions. So, but we call this is the oxidizer feed line and this is the fuel feed line. The fuel feed line is designated by 1 and the oxidizer feed line is designated by 2. Okay. So, the mixture fraction Z is essentially the ratio of M1 dot divided by the total M dot, that is M1 dot plus M2 dot. Okay. So, this is the I will just write it down, Z, the local mixture fraction is defined as M1 dot divided by M1 dot plus M2 dot. So, this is the mixture fraction. So, now this can be taken up in more details, that the YFU, that is the unburnt fuel mass fraction, then is essentially YF1, that is the fuel mass fraction in the stream 1 times Z. Why is it so? This is because what is YFU? YFU is essentially M dot of F divided by M1 dot plus M2 dot, okay, and that is equal to M dot of F divided by M1 dot times M1 dot by M1 dot plus M2 dot. Okay. So, M dot F minus by M1, that is what is the mass fuel mass flux, okay, that is going on inside through the feed line 1, that is YFU, okay, YF1 essentially times this is Z. So, that is why YFU, that is the unburnt fuel mass fraction that is going in, is essentially YF1 times Z. Okay. So, the total unburnt fuel mass fraction that is entering into this combustor is essentially given by YF1 times Z. Okay. Similarly, the oxidizer the oxygen mass fraction that is entering into the combustor is essentially YO2 dash 2, that is the oxidizer mass fraction in the second line in the oxidizer stream times 1 minus Z. Okay. And then combining this, one can obtain a generalized definition of a mixture fraction in terms of the mass fraction of the fuel and the oxidizer, okay, and this is given by Z. A mixture fraction at any point in space inside the combustor is given by nu, I will come what nu is, times YF minus YO2, that is the local mass fraction of fuel times the and minus the local nu times the local mass fraction of fuel minus the local mass fraction of YO2 plus the mass fraction of the oxygen in the S stream or the oxidizer stream that is coming in, divided by nu times YF1, that is the fuel mass fraction in the fuel stream, plus the oxidizer mass fraction in the oxidizer stream. Now, this just work this out why it is so, but this you will, I promise you that this will turn out to be a very useful concept. So, even if it seems little bit awkward at the beginning, just you get accustomed to these notations and what it exactly means, and it will become your friend very soon. Okay. So, now as you see that here the definitions are y of u is essentially the local mass fraction of the fuel in the unburnt mixture, unburnt fuel mass fraction. Y of 1 is a mass fraction of the fuel in the fuel stream. These two are not necessarily same, because y of u is essentially is in the unburnt mixture, this is a mass fraction. Okay. Similarly, y of 2 is a mass fraction of oxygen in the oxidizer stream, and nu is very interesting, is the stoichiometric mass ratio. You saw this was this previously also, is essentially nu O2 dash times W O2 dash. This is the stoichiometric coefficient of oxygen times the molecular weight of oxygen divided by the stoichiometric coefficient of fuel times the mass fraction of fuel. So, how are these defined? These are like nu F dashed times fuel plus nu O2 dashed times O2 goes to nu P double dash product. Okay. So, these are the stoichiometric coefficients. Okay. Please keep this in mind. So, nu is essentially the stoichiometric mass ratio. So, the actual definition of Z is this, okay, but at any point inside the combustor the Z can be obtained from this. If you know the mass, if you know the YF and YO2, you can know this, but then this is not very useful. Then we are just algebraic combination of YF and YO2. What we essentially what we want to essentially do is that we essentially want to find out an equation of Z and then find out the YF and YO2 in terms of Z. That becomes very useful. Okay. So, if you remember that chambered flame solution, I mean this is a very generic solution, it is essentially can be called the equilibrium solution also. So, if you remember the chambered flame solution, it was like one side you have fuel oozing out and one side you have oxidizer oozing out, and then if you do the solution and project the solutions in the mixture fraction space, okay, so then you will see that if there is no flame, if you do not ignite, then the solution you will get is essentially like this, straight lines once again, because it is essentially a linear it will turn out to be a linear differential equations, partial or ODE depending on the whether you have time or not. If it is a steady, it will turn out to be essentially an ordinary differential equation as we have seen before. And then for a burning mixture you will have of course product formation. So, and you will have oxidizer going down up to the ZST and YF going up from ZST to going to 0 at ZST, and here you will have the solution of T2, that is if this is the T2 and this is T1. So, this you will have the solution like this. So, it is essentially very we just have to write this this thing in the you have to solve it, and then you just write it in terms of the Z. If you just solve for Z, you will get this thing. So, it is very simple, but you see that this just like in we had the idea that this gives you is that just like we solved the 1D chambered flame in space, the laminar 1D chambered flame in space, you can essentially have a solution in the mixture fraction space also, and it is equally representative. Okay. So, of course, you have the maximum temperature at the ZST, which is the stoichiometric mixture fraction value. Okay. So, what is the stoichiometric mixture fraction value? That is, if you put the stoichiometric numbers here, the mixture fraction that you get. So, if for ZST here, you will get these two essentially go out. Okay, and then we will essentially be left with this, and we will have that ZST is equal to essentially this thing. Okay. So, this is the so essentially this is the thing you get, and you can basically have this kind of simple laminar solutions in terms of Z also. You just take a look and you just do this solve this. I will not go into this again because we already did the solution of the 1D chamber flame. So, this is just one more step where you convert those solutions into the mixture fraction space. Okay. But then this is important because the solutions, you see that it gives you an idea that you can, using this mixture fraction, you can essentially go from the physical space in terms of X to the mixture fraction space, which is in terms of Z. So, now if all flames essentially have obtained this, then the life would have been simple. So, these you know exactly, you have essentially analytical results for this this 1D chambered flame, and you can write all flames to be essentially in terms of this. But of course that is not true, because you will see that why this temperature can essentially deviate to temperatures like this from the adiabatic flame temperature, and of course this is the T adiabatic flame temperature for the given mixture. Okay. So, now what we want to do is that, now that because of the fact that we have established that the mixture fraction is a very important concept, and you can essentially write the temperature, okay, or species or any reactive species as such as a function of Z. Okay, this gives you this idea that that is possible, that when you essentially have these solutions in terms of the mixture fraction space, and that mixture fraction is a concept scalar. So then the idea is that, so let's do some modeling in terms of Z, and first thing is to essentially find out how Z, this mixture fraction, is transported in a turbulent flow. Okay. So for that we need to essentially develop this kind of averaged equations, this Favre averaged equations for the Z and the transport equations of Z, and then what we will try to do is that we will try to use these solutions, these solutions, to essentially project this kind of temperature etc. Along the mixture fraction, use these solutions to essentially define local flamelets at different points in the flow in terms of the mean Z and the Z variance of Z. So that is what we will try to do. Okay. So the idea is that since from these pictures of the 1D flame, we find that a mixture fraction is a very revealing, it essentially acts like an independent variable, okay, in the framework of this 1D chambered flame. So you can write things like Y, mass fraction, temperature, etc. in terms of the mixture fraction. So those can be expressed as a function of the mixture fraction. Now of course the thing is that so essentially if you are told that at a point, if you have which is say burning, you have essentially a mixture fraction of say this value, okay. So then you know the temperature at that point is this, you know at a point the Z has this value, so then you know that the temperature, the mixture you know that the temperature at that point is the adiabatic flame temperature, okay. So this gives you a map of these different reactive scalars as a function of the mixture fraction value. So the idea is that first we have to know that in a given combustor at a particular point in space, what is my mixture fraction value. Now to know what is that mixture fraction value, you need to essentially solve a transport equation of Z. Like in a combustor, you want to know what is the particular point, at particular point what is the velocity, okay. So to know what is the velocity, you essentially need to solve for the continuity and the momentum equation, and maybe other equations also if you need to, if that is a coupled with density. So similarly, just to know what is that point, to know in the combustor what is my mixture fraction, because if I know my mixture fraction, then and if this solution, if I assume this solution holds, the simple solution holds in that at each points in the flow, then just by knowing what is the value of mixture fraction, I can find out what is the temperature, okay. So first we have to know what is the value of mixture fraction. Of course we are not interested in the instantaneous value of mixture fraction, rather we are interested in the average value of mixture fraction, and for that we need to first find out a transport equation that gives us the average value of the mixture fraction and its variance at a particular point in flow. So we need to first define a governing equation that will tell us essentially what is the how to find out the mixture fraction is transported, okay.